So in unit 4, the last unit, we're doing chapter 10, and then we're going back to chapter 4. So if you remember, we skipped chapter 4. We went from 3 to 5. So we're going to pick up chapter 4 at the very end. But for now, we're going to do chapter 10. So chapter 10 is called hypothesis testing. Hypothesis testing is a method for making a statistical argument. Okay? So I like this example. Let's say we're going to play a game. And I'm going to flip a coin. And if it lands on heads, you're going to give me $5. And if it lands on tails, I'm going to give you $5. Okay? So what if I flip the coin 100 times? How many times would you expect to win, and how many times would you expect to lose? About half, right? 50%, 0.5. Okay? So we would make an assumption that the population proportion of head coin flips would be 0.5, or 50% of them would be heads. Right? Okay, are you going to get exactly 50% every time? No. So you would expect 50%, but you know that you're just taking a sample of 100 coin flips. You could get something else, but you would reasonably expect that the coin flip would be close to 50%, right? So if I were to win 55 times out of 100, you would feel unlucky that you lost, but you wouldn't be upset with me for losing. What if I won 85 times out of 100? What if I flipped the coin 100 times and I got heads 85 times and you only won 15? Would you want to keep playing? Why not? So what? What'd you say? I got a rigged quarter. Right. So is it possible for me to get 85 heads out of 100 though? Yeah, but it's not very likely that I would be able to do that, right? Without cheating or, either I have a rigged coin, a weighted coin, or I've really practiced flipping coins. I can flip it on heads. I can make it flip the right number of times, whatever. So we make an assumption to start with that the proportion of heads is 0.5. And then we do our experiment, take our sample, and the sample does not agree with that. Right? So what we will conclude is that what's most likely is that the assumption that we made is incorrect. That the assumption that we made that the proportion of heads is 50% that's not correct. It's got to be higher than that in order, if we get 85 heads out of 100. Let's see how rare that is. So that's a binomial problem, right? It's also normal, but let's look at the binomial distribution. 100 coin flips. If we assume P is 0.5, what's the probability of getting 85 or more out of 100? So what is that? So it has this E negative 13. What does that mean? And you move the decimal to the left 13 places, right? So that's a 0, 12 more zeros, and then a 2. Okay? So that probability is extremely low. So because that probability is so low, we're going to be skeptical that this could happen, right? What if I said 55? Remember I said, what if it was 55 instead of 85? Well, for 55, it's 18%. It's about 1 in 5 times. So If it's 55%, you're going to think, I just got unlucky, right? I just got unlucky. I'm not going to get a baseball bat and beat up Mr. Willman, right? But if it's 85 or more, you're thinking about getting the baseball bat. So what we've got to do is formalize this process. So we have to be able to draw a line. You know, where is the line between I think I just got unlucky to now I don't believe that it's a fair game and I'm going to get the baseball bat? Does that make sense? So that's what we're going to do in this chapter. We're going to, you know, go through all the pieces of this test, this hypothesis test, and we're going to draw the line. And if we cross the line, we're going to say we don't believe the assumption is correct. We believe something else is true. Okay? All right. So the first section is called the language of hypothesis testing. We're just going to go through the parts and kind of how it works. Okay? And the, you know, what do you say when your sample goes one way or the other? So hypothesis testing is a procedure based on sample evidence and probability used to test statements regarding a characteristic of one or more populations. We test claims about population proportion, population mean, and population standard deviation. We're only going to do proportion and mean in this class, just like confidence intervals. Okay. We're not going to worry about the standard deviation, but you could do standard deviation. We test these types of statements with sample data because population data is really hard to get. You could not have a recording of every coin flip that I've ever done, right? And how many heads there were. You would not know that. There's no way for you to figure that out. But you could take a sample, right, and see. So since we have only sample data, we don't have population data, we cannot prove that anything's true or false. Okay? We can only provide evidence to support something or not. So we can support statements with evidence, but we can't prove that anything is true because we don't have all the data. You could not prove that I cheated just based on the sample. You know, just based on the fact that I got 85 heads out of 100, that does not prove that I cheated. Okay, it just means you've got a lot of evidence that points that way. Does that make sense? Okay. Because it's still possible that I didn't cheat, that I just got really lucky and got 85 heads out of 100. It's possible that happened. It's just very, 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 very rare, right? That's what makes us skeptical of it. Okay, so we have actually two hypotheses, and they compete with one another. The first one's called the null hypothesis. The null hypothesis is always a statement that contains equality. It's always a statement that something is equal, to a parameter is equal to some number, and it is the assumption that we make in the beginning. So we assume something's true. In our example, you know, our null hypothesis is that the game was a fair game and that the population proportion of heads is 50% or 0.5. So the null hypothesis always contains equality, and it's always about a parameter. So it's always a parameter equals a number. The alternative hypothesis, it's H sub 1. It's always a statement that's something other than equals. So it could be either greater than, less than, or just plain not equal. Depends on what the researcher's trying to prove, or not trying to prove, but trying to supply evidence for. So usually, you know, if you're doing a hypothesis test, your research objective is usually the alternative hypothesis. So it's always greater than, less than, or not equal to. In our example, the alternative hypothesis is that it's not a fair game, that Mr. Willman is cheating. Therefore, the proportion of heads is greater than 0.5. And you have to, it's always the same number here. You always use the same number in both hypotheses, but the null always has equals, and the alternative is less than, greater than, or not equal to. Now, I said we're going to draw a line, and if we cross the line, we're going to say we don't believe the assumption is true. So when we talk about that, we're talking about the null hypothesis. So if I got 55 heads out of 100, you're not going to say, I don't believe this is true. You're just going to say, in this sample, I got unlucky. So even though the sample proportion was 55%, and that's bigger than 0.5, it has to be significantly bigger than 0.5 in order for you to say, I don't believe this is true. It has to be in the tails of the normal distribution. Okay, the tails are the ones on the very outside, the very low probability outcomes. It has to be one of those in order for you to say, I don't believe this thing's true. Okay, and if that's true, if you have a sample proportion that's significantly bigger than 0.5, like 85 out of 100, then you say, I have evidence to say I don't believe this is true. I support this statement. My evidence points to the alternative instead. Okay, but it has to be significantly greater. So let's see if we can identify these hypotheses. It says, according to the Center on Philanthropy at Indiana University, the mean charitable contribution per household among households with income of $1 million or more in the U.S. in 2005 was $17,072. A researcher believes that the level of giving has changed since then. So according to a study, or this group, the Center on Philanthropy, in 2005, the mean was $17,000. Now it's 2018. We're going to do our own study. The researcher thinks that this has changed. So the null hypothesis is always a statement about equals. Here we're doing a test about population mean. So we're going to use mu. And the null hypothesis is we're going to assume that there has been no change. That it's exactly what it was in 2005. So we're going to use null hypothesis mu equals $17,072. The alternative hypothesis is the goal of the research. We want to see if it's different now, and not just slightly different. We think it's significantly different. So we're going to test. The alternative hypothesis is that mu is not $17,072. And why did I use not equal to? Because it just says has changed. It didn't say it got lower or it got higher. It just said change. It's just different. So we're going to use not equal for those statements. So this is the assumption. This is what we're trying to show in our research. And we either have enough evidence or we don't. Okay? The evidence will come from the sample. Number two, according to the Center for Disease Control and Prevention, 19.6% of children aged 6 to 11 years old are overweight. A school nurse thinks the percentage of 6 to 11-year-olds who are overweight is higher in her school district. The null hypothesis is the assumption that there's no difference. There's no change. It's the same. So it's going to be P, its population proportion, is equal to 0.196. Or 19.6%, but we write population proportion as a decimal, okay, decimal form. So the alternative is that it's not the same. And in fact, we're given a direction here. The school nurse thinks that it's higher in her school district. So the alternative hypothesis is that P is greater than 0.196. And if she takes a sample of students in her school district, and the sample proportion is close to 0.196, even if it's higher, it's not enough evidence to say this is not true. The percentage in her school district has to be significantly higher. If it's significantly higher, so that the probability of it happening is very low, if we make this assumption, then we're going to say, well, now we don't think the assumption is true for her school district. We think it's higher. If she would weigh every 6 to 11-year-old in her school district, she wouldn't need to do the hypothesis test. Does that make sense? So she has to take a sample. So now she has to do this hypothesis test to see if her results are significant. Because sample proportions will vary, right? Population proportion is fixed. But sample proportions vary. She wants to know if hers is significantly higher. Okay. So there are 3 options for the alternative hypothesis: less than, greater than, or not equal to. And those determine the type of test that you do. And the type of test is, where do you draw the lines on the normal distribution? So the 3 types are two-tail test, left-tail test, and right-tail test. If your null hypothesis is parameter is not equal to some value, then you do a two-tail test. And what that means is, in the normal distribution, you're going to pay attention to both tails on the outside, just like you do with a confidence interval, right? You have these 2 tails on the outside. The two-tail test says the tails on the outside are the improbable portions of the distribution, and if your sample is in these improbable portions, then the assumption that you made is probably wrong, so we're going to reject the null hypothesis. Anything in the middle here is close enough to the null hypothesis that, we're not going to make that statement. We're not going to say the null hypothesis is not true. So for instance, let's look at the right-tail test. So if the parameter is greater than some value, if that's your alternative hypothesis, you use a right-tail test. So the right-tail test, you just pay attention to the right tail. That's a bad picture, but you use a right-tail test for this alternative hypothesis. So let's say that we look at our example. We assume that the population proportion is 0.5. If we look at the distribution of all sample proportions, that would be the mean. That would be the mean of the sample proportions, 0.5. Our sample proportion is 0.85, which is way over here in this tail, this right tail. And this is where we say, if we get past that line, that's far enough. Okay. How do we know where this is? We'll find a critical value, just like we did for confidence intervals. And if we have parameter is less than some value, we use a left tail test, so we're going to pay attention to the left tail. So this is two-tail test, right tail test, left tail test. So if our sample statistic, our sample mean or our sample proportion, falls in these tails, then we're going to say that's enough. We don't believe the null hypothesis is true. We're providing evidence for the alternative hypothesis. Okay. And anything that's not in the tails, we're going to say, well, that's close enough. So, it's not enough. It's not far enough away for us to say we don't believe it. Just like 55% was not far enough away from 50% in order for us to say we don't believe that it was a fair game. When it gets to a certain point, though, the probability of that thing happening is so low that we say, okay, that's super rare. Maybe it's not a fair game. Okay, so then we reject the null hypothesis. We support the alternative. Okay. But we could be wrong. So like I said, it's possible that I just got lucky and I flipped a coin 85 times out of 100 on heads. So that means there's error involved. We can't be 100% sure. We don't have the population data. Sample data varies. So there is some error involved. So there are two types. Type 1 error is when you reject the null hypothesis when the null hypothesis is true. So if it was a fair game and I just got lucky and you beat me up with a baseball bat, then you've made a type 1 error. You've said it's not a fair game even though it was, I just got lucky. Okay. Type 2 error is when you do not reject the null hypothesis when the alternative hypothesis is actually true. So if I cheated and you decided, let's say I cheated and I got 55%. It wasn't a fair game, but I only won by a little bit. Then, you're not going to reject the null hypothesis. You're going to say he just got lucky when he actually cheated. So that would be a type 2 error. Okay. So let me draw a picture. So in a hypothesis test, there are 4 possibilities. So the null hypothesis is either true or it's false. It's either true or it's false. If this is false, then we say the alternative is true. Okay, so and then we either reject the null hypothesis or we don't. So if the null hypothesis is true, we should not reject it. So that's a check mark. That means the test did its job. If the null hypothesis is false, we should reject it. So that means that one is what's supposed to happen. Okay? That means the test did what it was supposed to do. If the null hypothesis is true, but we reject it, then that is a type 1 error. And if the null hypothesis is false and we do not reject it, that's called a type 2 error. So which error is worse, in your opinion, to make? So type 1 error is, maybe someone says this thing is true, and you say it's false, and it actually was true. Okay? The type 2 error is this statement is false, and we say, I don't have enough evidence to say that it's false. I just don't have enough. So which one is the worst error to make? Type 1, right. So the best analogy for these errors is our court system. and this is the way it's supposed to work out. I'm not going to claim that it works this way all the time, but it's supposed to work this way, where the assumption that you make is the defendant is innocent. And the prosecution has to have enough evidence to prove that false. Okay? And if you don't have enough evidence, you do not say the person is innocent, you just say not guilty. You don't prove their innocence, you just don't have enough to prove that they're guilty. Okay? So it's going to work the same way. If you make a type 1 error, that is like putting an innocent man in prison. They were actually innocent, and you said they were not, and you found them guilty. Okay. The type 2 error is setting a guilty man free. They were actually guilty, but we did not have enough evidence to convict them. So that is a type 2 error. Okay. So type 1 error is the worst one to make in our court system too. That's what it's supposed to be. It's supposed to be hard to convict. That's why you have to have a unanimous jury decision. But what if we want to make this type 2 error, or this type 1 error, just go away completely? What would we have to do? We'd have to make it so hard to convict someone that we would never convict an innocent man. We'd have to make the standard so difficult. I think you could probably find these statements in the Bible. You know, certain people, you had to have 100 witnesses to convict somebody. You know, that's unreasonable, right? You would never convict anybody, you know, if you had to have 100 witnesses, right? So if you make it so hard to convict someone that you eliminate the type 1 error, what happens is you will never convict. You'll make the type 2 error more often. It'll be so hard to convict someone that you'll let a lot of guilty people go free. Does that make sense? So if you make it so hard to reject the null hypothesis by making the type 1 error go away, you'll make more type 2 errors. So there's a balance that you have to weigh. Okay? So we want to pick low probabilities of making the type 1 error, but we don't want to make them too low, because we'll make more type 2 errors. We'll not reject when we should have more often. Okay? So we control the type 1 error, but by controlling the type 1 error, we also control the type 2 error, because they're related. So the probability of making a type 1 error is that area in the tails, in the two-tail test, the right tail test, the left tail test. Whatever area is in the tail, that is the probability of making a type 1 error, and we call that alpha. You know, same as we did with confidence intervals. That area in the tail we call alpha, and it's got a name in hypothesis testing. It's called the level of significance. So you want to pick an alpha that's small, usually 10% or less. So the standard ones are 0.01, 0.05, or 0.1. So 1%, 5%, 10%. And how do you choose which one? Usually you choose based on the consequences of making a type 1 error. If the consequences of making a type 1 error are high, then you make the significance level low, like 0.01. If the consequences of making a type 1 error are low, then we can raise that significance level higher, and then that'll help us not make as many type 2 errors. Any questions? That's a lot of stuff. Any questions? Okay. So let's look at an example. What does it mean to make these errors? So this says determine the null and alternative hypotheses, explain what it would mean to make a type 1 error, and explain what it would mean to make a type 2 error. So this says federal law requires that a jar of peanut butter that is labeled as containing 32 ounces must contain at least 32 ounces. A consumer advocate feels that a certain peanut butter manufacturer is shorting customers by underfilling the jars. So the null hypothesis, so well, our only two choices are proportion and mean. So I think we'd have to use the mean here. We're going to say, well, let's assume that the mean is 32 ounces. The consumer advocate feels that a certain peanut butter manufacturer is shorting customers, so we're going to assume that, or we're going to test to see if that mean is actually less than 32 ounces. Okay. So what would it mean to make a type 1 error? So a type 1 error would be rejecting the null hypothesis when it's actually true. Is you saying, we don't believe that they're filling these jars with 32 ounces, we believe it's less, when they're actually doing it the right way. Okay, so type 1 error would be rejecting the null hypothesis when the mean is actually 32. A type 2 error would be not rejecting the null hypothesis when they actually are underfilling the jars. Okay, they actually are underfilling the jars, but we don't have, our sample doesn't provide us that evidence that we want. So this is, you do not reject the null hypothesis when the mean is actually less than 32 and not equal to 32. So would the consequences for making a type 1 error be high? So this consumer advocacy group would probably publish this somewhere in a newspaper or a journal, or publicize it to the media that says, hey, they are underfilling their jars of peanut butter when they actually aren't. Okay, so you can decide how high that consequence is. It's not a good position to be in if you're the consumer advocacy group. You would not want to make that type 1 error, But it's not life or death, but it could be somebody's job. So it's relatively high, I think. Okay, so what does it mean after you decide to either reject or not reject the null hypothesis? So since we cannot prove that a hypothesis is true based on sample data, we never accept the null hypothesis. Our statements are always going to be about the alternative. We're going to decide whether to reject or not reject the null hypothesis, but our conclusion will be about the alternative. So we never say the null hypothesis is true. We either say we believe it's false or we don't have enough evidence to say it's false. We do not reject it. So when the null hypothesis is rejected, we actually support the alternative hypothesis. So one of the two, the two things are competing. So if we reject the null, we support the alternative. The alternative is what usually your research is about. So when the null hypothesis is rejected, we say there is sufficient evidence to support the statement in the alternative hypothesis. when the null hypothesis is not rejected, we say that there is not sufficient evidence to support the statement in the alternative hypothesis. We never say the null hypothesis is true. We do not know if the null hypothesis is true. We assume that it's true to run the test, and then we decide, do we reject it or do we not have enough evidence to reject it? But because we do not have the population data, right, we'll never know what the population mean or population proportion actually is. You know, we can get a good idea by making a confidence interval, but we'll never know exactly what it is. So let's look at this problem. It says the mean score on the SAT Math and Reasoning exam is 516. A test preparation company says that the mean score of students who take its course is higher than 516. What's the null and alternative hypotheses? So the null hypothesis is a statement that there's no difference between the two. The population mean is 516 for both groups, for everybody as a whole and the students who take this course. Right, they're all 516. And the alternative hypothesis is that the mean for the students who take this course is higher than 516. Meaning that they're doing a good job of preparing the students for this test. Right? That's what they're trying to show. So the research objective is tied up in the alternative hypothesis. They want to show that their students are doing better than the average for all students who take the test. So B says if the sample data indicate that the null hypothesis should not be rejected, state the conclusion of the company. So what that means is, whatever their sample mean is, it's not far enough away from 516 in order for us to say, yeah, we don't think it's 516. So that means they do not have enough evidence to support the alternative hypothesis. Okay? So if they do not reject the null hypothesis, then we say there is insufficient. And you can say not sufficient, you could say not enough. You know, all those things mean the same. The book likes insufficient and sufficient. So there is insufficient evidence to support that the mean is greater than 516 for their students who take the course. Okay. Well, what if we took the population mean? What if we were able to find all the scores for all the students who took their course? What if that mean was actually 522? What type of error has been made? So we did not reject the null hypothesis, and we should have. Type 2 error. So this is a type 2 error. We've made a type 2 error. If we tested the hypothesis at the 0.01 level of significance, what is the probability of committing a type 1 error? This is not a trick question. I actually told you the answer a few minutes ago. What's the probability of making a type 1 error if alpha is 0.01? What does that say right there? The level of significance is the probability of making a type 1 error I told you it was not a trick question. This probability is 0.01. There's no figuring out to do. That's just what it is, okay? Don't miss that on the test or on the homework. So if we wanted to decrease the probability of making a type 2 error, we made a type 2 error. And we're using this low level of significance, which lowers the probability of making a type 1 error. What if we want to decrease the probability of making a type 2 error? What do we do to that level of significance? We increase it. Good. Increase. If you increase alpha, you will increase the probability of making a type 1 error, but you will also decrease the probability of making a type 2 error. Okay, so, and there's no magic number, there's no magic bullet to make those ideal. You just have to look at the circumstances of your study that you're doing. What are the consequences of making the type 1 error? You adjust the alpha accordingly. We wanted to not get this type 2 error as often, that we need to raise the level of significance. Okay, that's 10.1. So now we're going to go into actually doing some hypothesis tests. We'll go through some examples. We'll do all the parts, show you how it works. So we're going to start with population proportion. 10.3 will be about means, just like 9.1, 9.2. We did confidence intervals for proportions. We did confidence intervals for means. We're going to do hypothesis tests for proportions and then means. So the method of hypothesis testing relies on the fact that if observed results are unlikely under a certain assumption, we conclude that we have made the wrong assumption. So the certain assumption is the null hypothesis. If something happens that's very unlikely, like getting 85 heads out of 100 coin flips, then we conclude we've made the wrong assumption. That means we reject the null hypothesis if that happens. So when observed results are unlikely under the assumption that the null hypothesis is true, we say the result is statistically significant. That's hard to say. Statistically significant, and we reject the null hypothesis. So it can't just be that our sample proportion is higher than 0.5. It has to be significantly higher. And how far is that? We're going to use standard deviations to figure out how far is far enough. Okay, but statistically significant means it has to be far away from the assumed value in the null hypothesis. So we assume that it was a fair game, 50% heads. We get something close to 50%, we're not going to get the baseball at bat after Mr. Willman, right? It has to be significantly higher than 50% heads in order for us to do that. So where is the line drawn? We're going to decide how many standard deviations away from that null hypothesis does the sample proportion have to be? And that is going to be our critical value. And the critical value is based on what type of test we do, left-tailed, right-tailed, or two-tailed. And based on our level of significance, that's going to be that area in the tail, or tails if we have a two-tailed test. So the critical value determines what is unlikely when doing a hypothesis test. So how far away does it have to be? So if we have a critical value of 1.96, that tells you that your sample proportion has to be 1.96 standard deviations greater than the null hypothesis in order for us to reject the null hypothesis. That's how far away it has to be. So some definitions, some terms that we're going to talk about. The test statistic. It's a value used in making a decision about the null hypothesis. The test statistic tells you how many standard deviations your sample proportion is from the null hypothesis. So if my critical value says I got to be 2 standard deviations away, then I need to know how many standard deviations away my sample statistic is. You know, if I've got 55 heads out of 100, I've got a p-hat of 0.55. How many standard deviations is that away from 0.5? That'll be the test statistic. The critical region are the tails. So in a two-tail test, it's the tails on the outside. If it's left-tailed, it's the tail on the left. And if it's right-tailed, it's the tail on the right. Alpha is the area in that tail, or tails. And the critical value is the z-score that separates that tail from the rest. So let me draw a picture, or I'll draw a few pictures here. Let's do two-tail test. So there are 2 tails. Those tails together is alpha. That's the significance level. Just like with confidence intervals. Okay? Just like with confidence intervals. And that means the area in one of these tails is half of that, and the critical values are the z-scores that tell you where those areas start. You know, where does the critical region start? And you know, it has another one over here on the negative side. For confidence intervals, we only used one of these because we added and subtracted it when we found the confidence interval. We added and subtracted the margin of error. But with critical values in hypothesis testing, in the two-tail test, we use both of those because we want to see where the test statistic falls. Okay. All right. Let's do left-tail test. We only look at a left tail, and that area is still alpha. So we don't divide this by 2. So this is different than the confidence interval. We don't divide this by 2 on a left tail test. And the critical value is where this area is. It turns out to be the negative of z sub alpha. And we're going to use that normal calculator in StatCrunch to find these critical values, just like we did with confidence intervals. And then right tail test. We have a right tail. The area in that tail is alpha. The critical value is where does that tail start? And it's the z-score that has alpha area to the right. So let me just go further here. If we're doing a test about population proportion, we're going to assume the proportion is somewhere, like in our example, we assume that it's 0.5. And 0.5 is the mean. So in the standard normal distribution, the mean is 0. So when we find our critical value, we're just looking at the standard normal distribution at 0. You know, centered at 0. And when we find our p-hat, let's say it's 55%, 0.55, we can find the test statistic for that, which is just what's the z-score for that. You know, subtract the mean, divide by the standard deviation, see what the z-score is for that sample proportion. And if that test statistic is here, sometimes we call it z naught. If it falls in the critical region, we reject the null hypothesis. If it's somewhere close or somewhere other than the critical region, if it's here, we don't reject it. It's not far enough away. Okay. So we're going to compare the test statistic and the critical value when we make this determination. All right, so determine, make this bigger. I need the normal calculator. It says determine the critical values for a two-tailed test regarding a population proportion at the 0.01 level of significance. So when a two-tailed test, it's just like a confidence interval. Alpha is the area in both these tails. So if alpha is 0.01, what's alpha divided by 2? 0.01 divided by 2, 0.005. So I need the two critical values that have 0.005 area to the right and to the left. Let's say negative 2.58. If I go to the right, it's the positive version. So the critical values are these two. You have two of them, one on either side. And I just use the normal calculator, just like we've been doing for a long time now. Okay. Just like you're going to have to do on the test if you haven't taken it yet. So number 2 says determine the critical value for a left-tailed test regarding a population proportion at the 0.05 level of significance. So if it's left-tailed, there's only one tail, and that's the area in the tail, alpha. So I don't have to do two of these. So I don't have to do this twice. I don't have to divide anything by 2. I just go to the left. I'm going to put in 0.05 as the area to the left. So negative 1.64. If it was a right tail test, I would use alpha as the area to the right, and I wouldn't divide it by 2 because I don't have 2 tails. Just have one tail. Are there any questions? I'm going to stop here. We got a lot to go, but I think we can try to finish it next week.